Hi, everybody. Again, we are meeting to discuss some questions which students encounter in paper one exam, which is more considering the knowledge that you gained in the first months in the first unit, algebra and patterns. So, in the first video, we talked about the sequences, series, and their applications. Today we go again. We are going to continue this topic, and we are going to talk about proofs and combinations. So, if we talk about the proofs and combinations, it's important to notice that uh, these formulas. So, again, we should know what is the combination of R elements out of N elements. So, you can see this formula here. It's important one because it's used all around when we do the expansions and also the binomial expansion type. So sometimes we use this writing, sometimes we use this writing. So both of them are correct to use. So that depends on which one is easier for you to use, but you should be aware that they are the same thing. So, and in expansion, we have such a formula with n natural. So let's start from the first type of exam style questions. So let's suppose we have an expansion. It's a binomial expansion, y plus 1 to power 12. You can see that we have here unknown coefficients, and we need to find one or two of these coefficients. So actually, if we expand this, if we do this expansion, it should be something like this. Y plus 1 to power 12 is equal. So it's actually C12 0, y to power 12, 1 to power 0 plus. I'm going to write everything here because it's easy if you tackle the problem when you have the data on the data visually. So the second one would be 12 combination 1, so y to power 11, 1 to power 1. So plus the third one would be 12 to a combination of two elements out of 12, y to power 10 and 1 square. So it goes like this until the last term. So we are interested in A and B. Seemingly you have here A and B. So A should be, from this calculation, A should be the coefficient of y to power 11. So it is 12 combination 1. So it is, 12 factorial divided by 1 factorial times 12 minus 1 factorial. This is by definition. It's equal 12 factorial over 1 factorial is 1, 12 minus 1 factorial is 11 factorial, and by canceling, you get 12 here. So A is 12. But we already knew it because if we expand to the power of 12, so the second coefficient should be 12 here. It's obvious. So if you want to find B here, let's find B. So B would be equal. We had it, so it's the coefficient or corresponding coefficient at y to power 10 should be 12 combination of total 12 elements. So combination of two elements out of 12. So this is the coefficient of y to power 10. So it's equal to 12 factorial divided by 2 factorial times 12 minus 2 factorial. In this case, we're going to get 12 factorial divided by 2 times 10 factorial. Actually, 12 factorial and 10 factorial cancel each other. We get 11 times 12 divided by 2. 12 divided by 2 is 6, so it's going to be 66. So B is 66. Actually, by this way, we can find all coefficients here. But in the class, we also mentioned another method. We always know that this is 12. Yeah. And to find b, we multiply 12 by 11. 12 times 11 divided by 2. So it's going to be 66. If you want to find c, then in this case it's going to be 66 times 10. So if you want to find c, 66 times 10 divided by number of elements, 1, 2, 3. So in this way, we can find all the coefficients. You can check it with combinations also. You know the formula, so I would recommend to check it also. You know this, so we can use also this one. But preferably in the exam, it's better to do with combinations. So the second type of combination expansion, binomial expansion using combinations, is the question of this type. In the expansion of a plus k to power 5, where k belongs to real numbers set, the coefficient of the term in a cube is 80. Find the possible values of k. So if we expand it, if we apply the previous formula here, it's gonna be again combination of 0 elements out of 5, a to power 5, k to power 0, plus combination of 1 element out of 5, a to power 4, k to power 1, plus combination of 2 elements out of 5, again a cube k squared, and it goes like this. The final one would be 5 combination of 5 elements. So a to power 0, k to power 5. So which is, these coefficients are 1. That's when we expand, we use 1 there. So according to the question, we are requested to find k, but we know that coefficient of the term in a cube is 80. We know this. So coefficient of a cube, we are talking about this term. So it is 5. It's a cube k squared is equal 80 a cube. So we can cancel a cubes. So this one is 5 factorial out of 2 factorial times 3 factorial, which is 5 factorial cancels with 3 factorial is 4 times 5 divided by 2, which is 2 times 5 is 10. So actually 10 k squared equals to 80, k squared equals to 8. And from here we get that k equals to plus minus under root 8. So we can have two values, possible values for k in this expansion. One of them is plus under root 8 and the other one is minus under root 8. So let's continue with the next one. The next types of questions regarding the proving. Proving is included in your exam. So we know several types of proving. Actually, we learned direct proof, proof by mathematical induction, and also, if you remember, we learned proof by contradiction. So I'm going to demonstrate some questions regarding proofs. Prove that the sum of first n odd numbers is n squared. So odd numbers are 1 plus 3 plus 5 plus 7, of course, plus plus 2n minus 1. You know that the general formula for the odd numbers is 2n minus 1 is equal to n squared. Actually, we have to prove this one. So how to do? We can prove it with several ways. The first way that I want to demonstrate is by proving it by direct proof. So we know we can do like this. Actually, we can use the general formula for Sn, which is u1 plus un divided by 2 times n. u1 is 1 plus the last term is 2n minus 1 divided by 2 times n. So actually we have 2n divided by 2 times n, which is n squared. However, we can do this proof in another way also. Look, we are going to use this proof by Gauss method, which famous mathematician Gauss used at school for these types of sums. So we denote it by Sn. What I do here, I write from back to forward, the same numbers from back to forward. So it's going to be 2n minus 1, again, plus 2n minus 2, plus 2n minus 3, sorry, because the previous number before 2n minus 1, if 2n minus 1 is the odd number we know, then odd number before it, it's 2n minus 3. And we go like this until 1. Sn doesn't change because, you know, we can change the order in the addition. So we add these two sums, what we get, 1 plus 2n minus 1, it's 2n. 3 plus 2n minus 3 plus 2n. So all the time we get here 2n. You can check it for several ones. So on to n equals, here we get obviously 2 Sns. So how many 2n's we have here? We can notice that there are n such 2n's. So n times 2n equals to 2Sn. So you can cancel 2's here. So Sn equals to n squared. Or you can think some other ways to find these sums also, but these two ways are more reasonable here to apply because you have a good reason to explain how you get these things here. Now let's do the same proof, but this time using mathematical induction. Prove that the sum of first and odd numbers is n squared. We have to prove it by mathematical induction. Let's see what we have. We have 1 plus 3 plus 5 plus so on plus 2n minus 1 equals to n squared. So what is the idea of mathematical induction or proof by induction is that the first step here, we are going to have 3 steps. The first step here is to check for base number. We choose n equals to 1, the starting number. We look here. So if we take n equals to 1, there is only one number. We don't add here anything because we are talking only one term. Equals 1 squared. Let's check it. It's correct. 1 equals to 1 squared. So it is correct. Okay. So the first step was checking. The second step is that we made an assumption n equals to k plus 1. So we make an assumption for n equals to k, and the third step we are going to prove that n equals to k plus 1. Also for this k plus 1, also our statement holds true. So before that, we are going to make an assumption for n equals to k. So what does it give us? We assume that 1 plus 3 plus 5 plus so plus 2k minus 1. So obviously instead of n we place k is equal to k squared. We assume its validity. We assume that it is true. We need to prove the same thing for third step, n equals to k plus 1. So let me clean the board. I will have to write our assumption here for the second step again, plus so plus 2k minus 1 equals to k squared. You can see. And what we have to prove? We have to prove for n equals to k plus 1. So actually what we need to prove by formula 1, we need to prove 1 plus 3 plus 5 plus so plus 2k minus 1. And the next one, you see, k plus 1 term. So the next one is 2k. Instead of k, you place k plus 1. You're going to get 2k plus 1. So after 2k minus 1, the next odd number is 2k plus 1. It should be equal. We have k plus 1 elements here, so it should be equal to k plus 1 squared. So what I'm supposed to do actually, you can see here that we have 1 plus 5 plus so plus this sum. This sum actually we assumed to be k squared in the previous step, if you remember. So instead of this sum, we can place here k squared plus, you can have 2k plus 1. So we know from algebra that it's 2k squared plus 2k plus 1, and it's perfect squares expansion. It's k plus 1 squared. Actually, we got it done. It is k plus 1 squared. We wanted to prove it. So this is called a mathematical induction. Again, for proving mathematical induction, we need the first step is n equals to 1. The second step, assumption that n equals to k holds 2. And the third step is to prove for k plus 1. So the next type of proving also involves direct proof. But this type of proof is also used for proving some divisibility statements. So some statements about the division by some numbers. Look, consider any three consecutive integers, n minus 1, n, and n plus 1. Prove that the sum of the squares of these three integers is never divisible by 3. Let's do it by direct proof. So n minus 1 square, what we have to do, plus n square plus n plus 1 square. Yeah. Even if we are not given these numbers, we have to be aware that if we are talking about three consecutive integers, we can take such order, or we can take n plus 1, n plus 2. So what we do when we expand these brackets, we are going to get n squared minus 2n plus 1 plus n squared plus n squared plus 2n plus 1. You can see here minus 2n plus 2n, they will cancel. We have n squared, n squared, n squared. So 3n squared, it's good because 3n squared is divisible by 3, but we need to show that it is not divisible by 3. Plus, you can have 1 and 1 together, it's going to be 2. So we have actually 3n squared plus 2. Obviously, such numbers are not divisible by 3 because, 3n squared is divisible, but 2 is not. Actually, it's the remainder when we divide. So there is no way that this number is divisible by 3. So what we have done by direct proof, we have shown that the sum of these number squares of these numbers is not divisible by 3. So now let's see another example where we are going to use proof by contradiction. Prove the following statement for all integers n. If n squared plus 2n plus 5 is odd, then n is even. Let's assume that n is not even. Let's assume that n is odd. So actually, we are taking the contradiction here, contradictory statements. N is odd. Then if n is odd, then obviously it should be n equals to 2k plus 1. So we place here what we are going to get, 2k plus 1 squared plus 2 times 2k plus 1 plus 5. Again, what we do, we expand 4k squared plus 4k plus 1 plus again 4k plus 2 plus 5. So what we have finally, 4k squared plus 4k is 8k together, plus 1 plus 2, 3 plus 5 is 8. So looking at this result, we can notice that it is even number. It's obviously even because it's divisible by 2. But what was our previous assumption? Our assumption was that it is odd. So what we have done, we assumed that n is odd, and we came to the contradiction with what we are given. So actually, in this case, this contradiction shows that our assumption that n is odd is false. So if it is false, then what happens? There is another way, there is another choice, only one choice, that n is even. Because the numbers integers are odd or even. So they can be either odd or even. They cannot be in another way. So Actually, if it is not odd, if n is not odd, then it is obviously even. So that was all. I hope you enjoyed these videos. Do not hesitate to post your comments or questions, and do not forget to subscribe to videos to receive videos here. We are going to continue our topics still in the next videos. Thank you very much for watching.